All right, welcome back to another lecture. In this one, we're going to talk about inference on multiple means. We have previously talked about inference on multiple proportions, and we've also talked about inference on a single mean. We're now going to talk about inference on two or more means. And so we're going to cover three tests in this lecture. There is a data set that corresponds to this lecture that you can find on Canvas. So make sure that you have that downloaded and ready to go so that you can follow along with the examples. The tests that we're going to cover are the two-sample t-test, the matched pairs test, and those are both for testing two means. And then we have the ANOVA test if we want to test three or more means. Now, the difference between the two-sample t-test and the matched pairs test comes down to whether or not the samples that we're calculating the means of are independent or dependent samples. And so that's not a concept that we've really touched on in detail, so we should do that now. So let's talk about independent and dependent sampling first, and then we'll get into the hypothesis tests. So a sampling method is independent when the individuals selected for one sample do not dictate which individuals are to be in the second sample. A sampling method is dependent if it's not independent, right? Dependent samples are oftentimes referred to as matched pairs samples because the individuals in one sample have a matched pair in the other sample. Examples of dependent samples would be things like before and afters, where you're comparing each individual before some intervention to that same individual after the intervention. Others would be like husband-wife teams or twin studies or just anything where there's a link between the individuals in the samples, okay? If there is no link between the individuals, then the samples are independent. I think the easiest way to kind of get a handle on this is to just take a look at a few examples. So let's do that. Number one here says to decide whether these are independent or dependent sampling. So part A says, among competing acne medications, does one perform better than the other? To answer this question, researchers applied medication A to one part of the subject's face and medication B to a different part of the subject's face to determine the proportion of subjects whose acne cleared up. The part of the face that received medication A was randomly determined. So if we want to decide whether the sampling method used here is independent or dependent, what we should do is figure out what the two samples in question are, and then determine if the way the first sample was chosen automatically determined what the second sample would be. In this case, it's kind of a strange situation because there's really only one sample of people. You could kind of think of it like this. There's a sample of individuals to whom medication A is going to be applied, and then there's another sample of individuals to whom medication B is going to be applied. Now, it just so happens to be the case that those two samples of individuals contain the same individuals, right? Because each individual is going to have both medications applied to different parts of their face. These would be dependent samples because once you've chosen the individuals for medication A, you automatically get the individuals for medication B, namely the same group of individuals, right? So these are dependent samples. Okay. Part B says, do individuals who make fast food purchases with a credit card tend to spend more than those who pay with cash? To answer this question, a marketing manager randomly selects 30 credit card receipts and 30 cash receipts to determine if the credit card receipts have a significantly higher dollar amount on average. So here I think it's a little bit more clear that we have two distinct samples. One of them is a sample of credit card receipts and the other is a sample of cash receipts. There doesn't appear to be any link between these things. It seems like the researcher just went out and randomly chose 30 credit card receipts, and then completely independent of that, the researcher went out and chose 30 cash receipts. So these would be independent samples. There's no matched pairing going on. So you should pause the video and see if you can do parts C and D on your own. I'm going to go ahead and give you my answers to these. But part C says Joliet Junior College decided to implement a course redesign of its developmental math program. Students either enrolled in a traditional lecture format course or a lab-based format. There were 1,200 students enrolled in the traditional format and 300 enrolled in the lab-based format. At the end of the semester, researchers evaluated student performance. So the two samples in question would be the students enrolled in the traditional format and the students enrolled in the lab-based format. The students, as far as we can tell from this problem, from the statement of the problem, they decided which course to, which type of lecture to be involved in. It doesn't seem like the researchers, once somebody enrolled in a traditional format, they automatically determined something about somebody who would be in the lab-based format. And in fact, you might notice that the sample sizes are different. Okay, so there couldn't possibly be matched pairs, all right, because the sample sizes are different. So these are for sure independent samples. Okay, and part D, do women tend to select a spouse who has a higher IQ than their own? To answer this question, researchers randomly selected 20 women and their husbands. They measured the IQ of each husband-wife team to decide if there's a significant difference in IQ. These samples are dependent for sure. You have a sample of wives and you have a sample of husbands. Once the wives were chosen, the husbands were automatically determined, right? So yeah, these are dependent. And we've got those matched pairs, right? Husband-wife teams are matched pairs. Okay. So with that in mind, now that we know, how to tell whether samples are independent or dependent, we can talk about the difference between a two-sample t-test and a matched pairs t-test. For a two-sample t-test, we would run a two-sample t-test when the sampling is independent, okay? Just like with the two-sample proportion test that we introduced in the previous section, because we have multiple groups going on here, we have to use subscripts to distinguish between them. So x1 bar would be the sample mean of the first group, and x2 bar would be the sample mean of the second group, and so forth, okay, with the rest of those symbols. This is what a two-sample t-test would look like. By now, we're all familiar with the 5 steps that we take in hypothesis testing. So nothing really new here, except that we're testing means, of course, and we're trying to compare two means to one another. Checking conditions is not going to be a big emphasis of the course, but as far as conditions to check are concerned, we have to make sure that the samples are independent in order to run the two-sample t-test. And we need to make sure that the populations are normally distributed with no outliers. Or if that's not the case, then we need to have large sample size. And by large, we mean at least 30. So let's take a look at some examples. Number 2 here says a medical researcher contends that the lung capacity varies significantly between smokers and non-smokers. For a sample of 40 smokers, the mean lung capacity is 4.5 liters with a standard deviation of 0.4 liters. The mean lung capacity for a sample of 30 non-smokers is 5 liters with a standard deviation of 0.3 liters. At alpha equals 0.01, is there sufficient evidence to conclude that lung capacity is larger among non-smokers? If so, construct a 99% confidence interval for the difference in lung capacity. Okay, so it doesn't matter which group we call group 1 and which group we call group 2, as long as we remain consistent throughout the problem. So I'm going to go ahead and label the groups so that I'm sure that I'm staying consistent. Since the smokers were listed first, I'm going to call them group 1, which means that the non-smokers are group 2. Now, the null hypothesis is going to be that there's no difference between these groups, right? They have the same average lung capacity. mu1 equals mu2. The alternative hypothesis is the claim that the researcher is usually trying to prove, okay? And in this case, the researcher contends that lung capacity varies significantly. Specifically, we're asked to test if lung capacity is larger among non-smokers. So we want to know if group 2 has a larger mean than group 1. If that's the case, then of course group 1 would have a smaller mean than group 2. So the alternative is that mu1 is less than mu2. Now, what sample evidence does the researcher have to make this claim? Well, group 1, he went out and selected 40 smokers and found that they had an average lung capacity of 4.5 liters. He then went out and sampled 30 non-smokers and found that they had an average lung capacity of 5 liters. So the non-smokers, at least in his sample, the non-smokers had an average lung capacity that was half a liter larger than the smokers did. So that's his evidence. Now, the only way to know if that evidence is statistically significant is to compute the p-value. And so that's step 3. So to compute the p-value, we're going to go to artofstat.com. The app that we're going to use is called the Compare Two Means app. So let's write that down, that we're going to use the Compare Two Means. We should also indicate the statistics that we're going to feed into that app, right? So for group 1, our sample size was 40. Our sample mean was 4.5. And our sample standard deviation was 0.4. For group 2, it was a sample size of 30, a mean of 5, and a standard deviation of 0.3. So we'll go to the app and we'll enter all that information in and see what we get for our p-value. Okay, so let's head over there. Not that one. Okay, so if you just go to artofstat.com, you can follow the link, by the way, in the notes and get directly to the calculator that we're going to use here. But let me just show it to you this way. If you go to artofstat.com and then click on Web Apps, you can also download some mobile apps, right, and use your phone or whatever. But I'm going to show you how to do this with a web app. And then you're going to scroll down until you get to confidence intervals and tests comparing two groups. And what we want to do is compare two means. So that's this app right here. So we're going to click on that one. And let's go ahead and enter the information. We don't want to do an example from the textbook. We want our own example, and we have summary statistics, not raw data, right? So if you go to provide own, then it'll ask you for raw data, which we don't have, but we do have some summary statistics that we can enter. The response variable here was lung capacity. You don't have to give the variables a name, but it's helpful. Group 1 we said would be the smokers. Oops, smokers. And group 2 was the non-smokers. Okay, and then for group 1, we said we had a sample size of 40, a sample mean of 4.5, and a sample standard deviation of 0.4. For group 2, we had a sample size of 30. We had a sample mean of 5.0. And we had a standard deviation of 0.3. Now, we don't want a confidence interval just yet. I think we're asked for that in a follow-up question. What we want right now is a hypothesis test, which the app calls a significance test. So we'll click on significance test. And then, of course, for the significance test, we have to state what the alternative hypothesis is. In this case, we wanted it to be a left-tailed test. We wanted a less than sign. in our alternative hypothesis. And there you go. So very small p-value, right? Less than 0.0001. If you're asked for the test statistic, then here it is, right? It's this value right here next to the p-value. That's not going to be a big emphasis for me. What I'm really here for is the p-value, which is tiny, right? Very, very small. So let's write that down. So the p-value is less than 0.0001. With the p-value in hand, then we can make a decision. To make that decision, as usual, we compare our p-value, which is less than 0.0001, to alpha, which is 0.01. Our p-value is less than alpha, so we reject. Okay. So now we can write a conclusion. We are rejecting the null hypothesis, which means there's evidence to support the alternative, right? And that's what we would say. There is sufficient evidence to conclude, or to indicate, or something like that, to conclude that. And then I'm just going to, I think, take this statement: lung capacity is larger among non-smokers. Surprise, surprise. So that's the end of our hypothesis test, but then we were asked a follow-up question. We were asked if there's sufficient evidence, then construct a 99% confidence interval for the difference in lung capacity. So we can do that. To get our 99% confidence interval, we would go to the same calculator and enter the same statistics as we did for the hypothesis test. So I'm not going to rewrite all of that information. It's all here, right? All of this same stuff is what we would use to compute the confidence interval. So all we have to do is change the type of inference from a significance test to a confidence interval. We want a 99% confidence interval, so I'm going to slide this over to 99%. And there you go. So our confidence interval, you can see it here. You can also see it here. So we'll say it's about negative 0.727 to negative 0.278. Okay, liters, of course. So we weren't asked to give an interpretation of this interval, but if we were, we would say, well, we're 99% sure that the difference in lung capacity between smokers and non-smokers is somewhere between, 0.727 liters and 0.278 liters. The reason that these values are negative is because we're subtracting the non-smokers from the smokers, and non-smokers have a higher lung capacity. So in other words, if you do like 4.5 minus 5, you get negative 0.5, right? So this is just indicating that the fact that these are negative is just indicating that the non-smokers have a smaller lung capacity than that the smokers have a smaller lung capacity than the non-smokers do. And it's somewhere between, roughly 3/4 of a liter and 1/4 of a liter in lung capacity. So that seems like a pretty significant difference to me. Okay, that'll do it for number 2. Let's do another one. Now, this one has raw data, you'll notice, like right off the bat. So we'll have to run this a little bit differently in the app, but a lot of it's going to be similar to what we just did. So you should give the video a pause and see if you can work it out on your own. I'll go ahead and read through it and give you my solution. It says, in the Space Lab Life Sciences 2 payload, 14 male rats were sent to space. Because of course, of course we're sending rats to space, right? Upon their return, the red blood cell mass in milliliters of the rats was determined. A control group of 14 male rats was held under the same conditions except for spaceflight as the space rats, and their red blood cell mass was also determined when the space rats returned. The project resulted in the data listed below. Does the evidence suggest that the flight animals have a different red blood cell mass from the control animals at the 0.05 level of significance? We're asked also to construct a 95% confidence interval for the difference in red blood cell mass. Okay, well, we can call the flight group Group 1 and the control group Group 2. And the null hypothesis would be that these two groups have the same red blood cell mass, right? There's no difference between them. The alternative would be that, well, we just want to test to see if the flight animals have a different red blood cell mass. So we don't need to run this left-tailed or right-tailed. We can just run a two-tailed test. We just want to know if they're different. Okay. Step 2 would be to collect our sample evidence, right? X1 bar and X2 bar. Now, we weren't given that information in the problem because we just have the raw data. But this data set is in Excel, and so you could use Excel to figure out what those sample means are. In fact, let's go over to Excel and do that. So to get the sample mean for the flight animals, we would use the equals average function, and then we can select our data and hit enter. So there's the average for the flight animals. For the control animals, same thing, equals average, and select our data and hit enter. So for the flight animals, it's about 7.88, and for the control animals, it looks like it's exactly 8.43. So 7.88 and 8.43. Seven 7.88, 8.43. This one should be exact. Okay. So that does seem to me to be like a pretty good difference. However, our sample sizes are fairly small. We've only got 14 individuals in each group. So with only 14 individuals, maybe this isn't quite good enough. We'll see. We've got to get the p-value to make that determination. So we're going to go to artofstat.com, and we will use the compare two means. So we'll use the compare two means app, and this time we're not going to feed it any summary statistics. We're just going to feed it raw data. So we'll enter the raw data, and then we'll be able to get our p-value. So let's do all of that. So first of all, what we'll want to do is copy. So Control C, and then we can paste that into the ArtofStat app. So again, I don't want to do an example from the textbook. I want to do my own. This time I do have raw data, so I'm going to click on Provide Own. And then I can paste the values from Group 1. Let me go grab the values from Group 2. Okay, Group 1 was the flight group, and group 2 was the control. And the response variable that we're measuring is red blood cell mass. Right, in milliliters. Okay. We're interested in a confidence interval, but not just yet. Let's do the significance test. And we did indeed want a two-sided test, so we will just leave the alternative two-tailed, two-sided, and there's our p-value, 0.1627. Okay, so we'll write that down, but while we're here, let's go ahead and get the confidence interval, since we know that we're going to be asked for it, right? So let's grab the confidence interval while we're here. Okay, so it looks like our 95% confidence interval extends all the way from negative 1.335 to 0.237. Okay, so just commenting real quick before we go over and write these things down. Again, if you look at the p-value for our significance test, this is a large p-value, right? This p-value is basically saying that if we assume that the null hypothesis is true, then there's about a 16% chance that we would obtain sample means as different as the ones that we've obtained. Well, 16% is not that small. It doesn't give us any reason to suspect that the null hypothesis isn't true, so we don't reject it, right? We're not going to reject the null. By the way, you may notice that the app computes the sample means for us, so technically you don't have to use Excel to do that, since it'll be done for you in the app. But yeah, we're not going to be rejecting the null. There's not sufficient evidence to say that there's a difference between the red blood cell mass of these two groups. And that's reflected in the confidence interval, because this 95% confidence interval contains 0, right? Which means we can't rule out that the difference between the groups might be 0. In other words, that there might be no difference between the groups, since 0 is within our interval. Anyway, let's write these things down. So our p-value is 0.1627. So our decision, 0.1627 is not less than 0.05. So do not reject H null. Okay, so there is not sufficient evidence to conclude that the space rats, rats, that the space rats had a different, okay, so I should be more careful. We know that the space rats in the samples did have a different mean, okay? But that's not enough evidence to say that space rats will always have a different mean. So we should say something more along those lines. So there's not sufficient evidence to conclude that space rats will always have a different red blood cell mass than control rats, I guess you could call them. Rats that aren't sent to space. So it doesn't seem to be the case, or at least we don't have enough evidence to say that it's the case that sending rats to space will somehow affect their red blood cell mass. So that's the idea there. Now, that said, again, we have a small sample size, and the difference here was, at least in the sample means, it was fairly large in my view, but not we just don't have enough evidence. It could be that there is a difference, and maybe if they doubled their sample size, assuming that they observed the same difference, if they had double the sample size, they probably would be rejecting the null hypothesis. So anyway, that's that. So that's the two-sample t-test. Again, that's for independent samples. If you have dependent samples, then we'll use the matched pairs t-test. Okay? And basically the reason that we even bother distinguishing between dependent and independent samples is because if you do have dependent samples, then you can run the matched pairs t-test, which typically will give us a better p-value than the two-sample t-test. It's only valid to use the matched pairs t-test if the samples are dependent. Okay, so you have to be careful. But if you have dependent samples, then typically we can get a smaller p-value when we apply the matched pairs t-test, which is why we kind of bother in the first place to distinguish between independent and dependent sampling. The idea behind the matched pairs t-test is that because the individuals in the two samples are matched pairs, you can subtract the values, the corresponding values from those samples, and end up with just a single sample, and then perform a one-sample t-test on the differences. Okay. We're not going to do any of that by hand, but I just thought you might want to know that that's kind of what's going on with the matched pairs t-test. For more information, of course, you can look at this online discussion. Okay. But this is how the matched pairs t-test will work. Okay. Looks pretty much the same thing as the two-sample t-test. We'll use the same calculator, compare two means, but there's a little menu across the top where we can change from the two-sample t-test to the dependent sampling. And you'll see it'll say two dependent samples along the top, and we'll want to click on that version of the app. So let me just give you a couple examples. Number 4 here says, a dietitian wishes to see if a person's cholesterol level will decrease if the diet is supplemented by a certain mineral. 7 subjects were pre-tested and then took the mineral supplement for a 6-week period. The results are as follows. Okay, so we have each patient before and after. We'll call the before group group 1 and the after group 2. It's really the same group of people though, so clearly these are dependent samples, right? Person number 1 had a cholesterol level of 210 before taking the supplement, and then 6 weeks after taking the supplement for 6 weeks, they had a cholesterol level of 190, right? So that seems like it worked for person number 1, okay? Worked for person number 2. For person number 3, maybe it had the opposite effect, but not by much. Overall, looking at the data, I would say it seems like the mineral works. But the problem is we have a small sample size here. So is this enough evidence, right? Is the evidence sufficient? Well, only one way to know that, and that's to run the test. So let's state our hypotheses. The null hypothesis is that the mineral does not work. The mean is the same for the two groups. They have the same cholesterol level before and after, okay? The alternative hypothesis is that the supplement does work. Now, if the supplement works, then we expect the cholesterol level of the group to be lower after they've taken the supplement. So we would expect mu2 to be smaller than mu1. In other words, mu1 would be greater than mu2. So looks like we're going to be running a right-tailed test. Step 2 is to gather some sample evidence. I'm just going to let the app compute the sample means for us, but let's not forget to write those down later so that we can see if our results make sense and everything. But just looking at the data, it certainly seems like the average is lower before or lower after than it was before. To get the p-value though, we're going to go to artofstat.com. We're going to go to the compare two means app, And then here, just maybe make a note that that you're going to use the dependent calculator. Okay. And we don't have any statistics to feed in. We just have the data. So we're gonna say entered or enter raw data. Okay, and that'll get us a p-value. Okay, I was just looking ahead, checking to see if we needed to get a confidence interval here, and it doesn't look like we're being asked for one. So we'll just get the p-value. So to do that, I'm going to first, let's go over to the cholesterol example in the Excel spreadsheet so I can copy and paste these. Okay, so I'm going to copy and paste. Let's do Control C. Oh, I need to reload this. So up here, we're in the Compare to Means app. Up here in the top menu, you're going to want to click on Two Dependent Samples, okay? And I don't want to run an example for the textbook. I'm going to provide my own. So I can paste the values from group 1. Let me go grab the values from group 2. So Control Shift down, Control C, Control V. All right. And so group 1 was the before taking the supplement. Group 2 was after taking the supplement. And the variable we're measuring is cholesterol levels. Again, you don't have to label these things, but it's kind of nice to. Anyway, its default setting is to give us a confidence interval, of course, but what we want is a significance test. Notice that they also give you like side-by-side box plots and stuff, which is really nice. We did not want a two-tailed test. We wanted to know if the after group had a smaller cholesterol level. So in other words, if the before group had a larger cholesterol level, so we wanted a right-tailed test. And so there's our p-value, 0.0641. Okay, 0.0641. Whoops. So our p-value, 0.0641. Okay. Well, 0.0641. It's a really close call, but it doesn't quite meet the threshold, right? It's not less than 0.05, so do not reject. H null. Okay, we're not rejecting the null hypothesis. And so we would say there is not sufficient evidence to indicate that the mineral lowers cholesterol. Is that how you spell cholesterol? Well, we'll go with it. I think that's right. Cholesterol levels. Okay. Oh, I forgot to write down the sample means. Let's see if it's still up there. So our sample means before 209 and after 209.9, and then after it was 194.3. 209.9. And then what did we say? 194.3. Okay, so again, I think that this is I think it is a fairly large difference. It's just that we only had 7 people in our sample, and so we weren't quite able to achieve statistical significance as a result of that. What does the p-value mean? Well, it means if we assume that the null hypothesis is true, in other words, if we assume that the average cholesterol level is the same before and after taking the supplement. In other words, if we assume that the supplement doesn't work, okay? If we assume the supplement doesn't work, then there's a 6.41% chance that we would observe this much of a difference before and after. Okay? So if we assume the mineral does not affect cholesterol, then there's a 6.41% chance, or maybe probability is a better word, but I'll just leave it. 6.41% chance that we would obtain a sample with a difference as large as the one we have observed. Is a 6.41% chance enough for us to say that maybe we shouldn't assume that the mineral doesn't work? Well, not in this case, because the threshold that was set for us was 5%, right? We needed a probability less than 5%. If we had used the 0.1 level of significance, then we would be rejecting the null hypothesis here. Okay, next one. Oh, I like this one. So it says, sports fans often complain that referees show preferential treatment to the home team. Below are the number of free throws attempted by the home team and the away team in 13 randomly selected games. Basketball games, I guess, right? Part A says, at the 0.05 level of significance, test the claim that the home team shoots more free throws than the away team. Okay. Again, just to emphasize, we're not testing here whether in this particular set of 13 games, the home team shot more free throws than the away team. What we're asking is if, in general, home teams shoot more free throws than away teams do. Okay? That's the claim that we're trying to test. We're trying to test to see if the population mean number of free throws for the home team is more than that for the away team. The null hypothesis, of course, is that no, there is no difference, right? They shoot the same average number of free throws. The alternative hypothesis is that, yeah, the home team, group 1, shoots more free throws than the away team, group 2. Again, we weren't given the sample means here. We'd have to calculate those ourselves, which we can let the app do for us in a second, or we could do it in Excel, however you prefer. Step 3 is to get the p-value. We're going to go to artofstat.com. We're going to use the compare to means app, and we want to use the dependent samples app, okay? And then, of course, we're going to enter the raw data. You might hear my dog snoring in the background there. Okay, we will be asked for a confidence interval in part B. So I'm just taking note of that so we can do them both kind of at the same time. Okay, let's see what we get. So first I'm going to go over to Excel so I can grab the data. This is the free throws example. You'll notice, by the way, that I keep trying to avoid taking the column title because I don't want those words to be in my data set. I just want the numbers, right? So I'm just selecting the numbers, Control Shift down, Control C. Okay, again, I want to click on 2 dependent samples. And I'm not doing a problem from the textbook. I want to provide my own. Okay, Control V. And let's go get the data for group 2. You could enter these manually as well, of course, if you prefer. Control V. Okay, this was the home team. This was the away team. And we're looking at number of free throws. Okay, so this is the setup. Okay, let's get the p-value. So running our significance test, we wanted to know if the home team shot more free throws than the away team. So we want a right till test greater. And yeah, look at that p-value, right? 0.0198. Also take a look at the sample means, right? For the home team, it was 31.62. And for the away team, it's 27.23. I'm writing these down so I don't have to scroll back and forth. Okay, so that does seem like a pretty substantial difference. You know, maybe a difference of about, 5 free throws or so. Okay. Let's get our confidence interval. So our 95% confidence interval goes from 0.245 to 8.524. All right, let's write those things down, make some observations. So our p-value is 0.0198. Zero 0.0198 is less than 0.05. So we reject the null hypothesis, right? There's only about a 1.98, so basically like a 2% chance. There's only about a 2% chance that we would observe a difference in sample means as large as this difference, if the null hypothesis were true. So that gives reason for us to kind of suspect that maybe the null hypothesis isn't true, because it's so unlikely that we would have observed this, okay, if the null hypothesis were true. So we reject it in favor of the alternative. And that's what we're going to say in conclusion. There is sufficient evidence to suggest that home teams shoot more free throws than away teams. So yeah, it seems like home teams, generally speaking, have a slight advantage in that sense, right? They shoot more free throws than the away team, which means that the referee is calling fouls on the away team more often than they're calling fouls on the home team. Okay. Well, part B says construct and interpret a 95% confidence interval for the difference in the number of free throws shot by the home and away teams, and then comment on the practical significance of this difference. So our 95% confidence interval, we've already computed that. And it goes from 0.245 to 8.524. So the home team shoots, the interpretation of this would be we're 95% sure that the home team shoots somewhere between 0.245 and 8.524 more free throws than the away team on average. 0.245 is obviously not very much, but 8.5 is, okay? So let's write down our interpretation. We're 95% confident that the home team shoots on average somewhere between 0.245 and 8.524 more free throws than the away team. What does that have to do with the practical significance? Well, what we're saying is that there's definitely a difference. Well, not definitely. We're pretty sure that there's a difference between the number of free throws that the home team and away team shoot. But on the lower end of the spectrum, it might not be that much more. On the other hand, it could be a lot more, right? So as far as the practical significance is concerned, I would say on the lower end estimate, there isn't much of a practical difference. Right? Because 0.245, it's like over the course of 10 games, the home team would only end up shooting 2 more free throws than the away team. And that just doesn't make a ton of difference, I would argue. But on the upper hand, end of the estimate, I would say there is a substantial difference. Because on the upper end, the home team is shooting 8 or 9 more free throws than the away team. That means they have the opportunity to make 8 or 9 additional points per game, which would make a huge difference, right? They would be at a huge advantage. So on the upper end, there is a substantial difference, I would say. Now, Part C asks an interesting follow-up question. Do the results of this hypothesis test show that referees show preferential treatment to the home team? And at first glance, it might seem like, well, yes, because after all, we rejected the null hypothesis, so the home team does shoot more free throws than the away team. And that means that the referees are calling fouls on the away team more often than they're calling fouls on the home team. So certainly that shows that referees show preferential treatment to the home team. But on the other hand, I think we would have to be a little bit more careful than that. And we would have to say, well, yes, this could be an indication that referees show preferential treatment to the home team. But it could also be the case that when away teams come to play, they just come in more aggressive, right? It could just be the case that they just play more aggressively because, I don't know, maybe they feel like, well, we're not on our home turf, so we have to show them, or whatever. They just come in and play more aggressively. And so they deserve to have more fouls called on them, right? That could be the case. So do the results of this hypothesis test show that referees show preferential treatment to the home team? Not necessarily, right? Not necessarily. right? It could be the case that home teams shoot more free throws because the away team deserves to have more fouls called on it because maybe they play more aggressively. This is an important lesson to learn. Generally speaking, it is the case that oftentimes in the real world, researchers will be trying to study something, but the thing that they're trying to study is maybe difficult to measure. Like it's really difficult to measure whether the referees show preferential treatment to the home team. So what the researcher will do is they'll identify some kind of proxy measurement that is easy to measure. In this case, whether or not the home team shoots more free throws than the away team. Okay, that's sort of like a proxy. The idea is, okay, if the home team shoots more free throws, then we have evidence that the referees are showing preferential treatment to the home team, right? This is kind of what the researchers were probably thinking. But you have to be careful because just because there's a difference in whatever proxy thing that you're trying to measure, it doesn't necessarily mean that that there really is a difference, in the actual thing that you are trying to study. Just to give you another example of this, so cholesterol levels are linked to heart disease, right? To risk for heart attack and things like this. And so cholesterol's on my mind because we were just looking at that cholesterol example. So for a long time, medical researchers thought, okay, if we can figure out a way to lower cholesterol levels, then that will decrease the likelihood that somebody will have a heart attack, right? Now, I'm not a medical professional, so you should take this all with a grain of salt. But as far as I understand it, what has actually happened is that we've developed all of these drugs and things that will lower cholesterol levels, but we have not seen a decrease in heart disease and heart attack and things like that. And so you can see a medical researcher maybe thinking, oh, this new pill that I've developed, it's going to help people avoid having heart attacks, right? When what it really does is just lower their cholesterol levels and does nothing to decrease their probability of having a heart attack. So this is the kind of thing that I mean when I say, it's important to distinguish between what the researchers were trying to show and what the results of their studies actually show. Okay? So anyway, so that's just a little nugget for you, but I think it's an important one. We have one more test to cover. So we've got one more test. We'll do two examples of the analysis of variance test, or the ANOVA test for short. And this test is used if we want to compare more than two means. Okay, so if we have three or more groups that we're trying to compare, then we'll run the ANOVA test. ANOVA stands for analysis of variance. The null and alternative hypotheses of an ANOVA test are kind of similar to the null and alternative hypotheses for a homogeneity of proportions test, only we're testing means instead of proportions, right? So what I mean by that is when we were testing multiple proportions, we had two different tests that we would run. We had the homogeneity of proportions test, which said P1 equals P2 equals P3, etc. And then we also had the goodness of fit test, which said P1 equals some number and P2 equals some other number, and so forth. And so what I'm trying to say here is that the ANOVA test is more like the homogeneity of proportions test than it is like the goodness of fit test. In fact, we really don't have an analog to the goodness of fit test for means. So we really just have the ANOVA test, which is more like the homogeneity of proportions test. In fact, you could call this test a homogeneity of means test rather than an ANOVA. But we'll call it ANOVA. Now, there are one-way ANOVA tests and two-way ANOVA tests. A one-way ANOVA measures the influence of one explanatory variable on one response variable. That explanatory variable might be split into multiple groups, right? So, for example, you could have like one of the examples we'll see will be like the brand of a certain porcelain repair kit, and the response variable is the strength of the bond that the repair kit makes with the porcelain. So, the explanatory variable brand, there could be 3, 4, 5 different brands that you're comparing, and so you might be comparing 5 different groups, but it's still only one explanatory variable, which is brand. Okay, so anyway, with the one-way ANOVA, you're comparing, you're measuring the influence of one explanatory variable on one response. With a two-way ANOVA, you're measuring the influence of two explanatory variables on one response. All right, so to use the chipped porcelain example, it's like brand could be one variable, and maybe like the temperature inside of the bathroom where you're trying to repair the chipped porcelain, like that might be a second variable. And so if you're trying to look at the influence that both of those variables have on a response variable, then you would run a two-way ANOVA test. Now, two-way ANOVAs are beyond the scope of this course, so we're not going to get there. But it does kind of beg the question, well, what if you have more than two explanatory variables? Or what if you want to measure the influence of an explanatory variable on more than one response? And there are other tests for these things. We have things like the ANOVA test. This is the multivariate analysis of variance test. We have the ANOVA test. This is the analysis of covariance test. But these things are also beyond the scope of the course. If you're interested in them, well, you should take more statistics. take some more statistics courses. We're just going to focus on the one-way ANOVA, and that's as far as we're going to get. One last thing to say before we get into looking at the test regarding the name analysis of variance. You may wonder, wait a second, I thought we were testing means. Why are we doing an analysis of variance, right, when what we want to compare are means? The reason it's called the analysis of variance test is because what we do in the analysis of variance is we look at how much variance there is within one sample, and we compare that to the overall variance between all of the samples that we're trying to compare. And the idea is that if there's only a little amount of variability within one sample compared to a lot of variability between the samples, then what that would indicate is that the data must be nicely separated into distinct groups. And what that would tell us as far as means are concerned is, okay, if you're separated into these distinct kind of chunks, then each chunk is going to have a different mean. They're not going to be all jumbled and mixed together, in which case they would have the same mean. Now, if you want more details about that, of course, you can look at this link and kind of read through the information there. I'm just going to go ahead and give you the test. Same steps as usual. We'll state our hypotheses. For the ANOVA, it's the null hypothesis is always that the means are all the same. The alternative is always that at least one of the means is different. We'll want to gather our sample evidence. The app that we'll use from ArtofStat will compute those sample means for us automatically. The app we're going to use is called the ANOVA One-Way, and the rest is history. As far as conditions to check are concerned, we have to have random samples. They have to be independent samples. The populations need to be normally distributed, okay? And the populations have to have the same variance. Now, that third condition is difficult to check, and it would actually require a separate hypothesis test in its own right to see if the variances are all the same. But in practice, what we'll do is we'll assume that this is true as long as the largest sample standard deviation is no more than twice the smallest sample standard deviation. And if that's the case, then we'll assume that that condition is met. As usual, checking conditions is not going to be a big emphasis of the course. Okay, so let's take a look at a couple examples. This one says, The data below show the shear bond strength for different repair kits for chipped porcelain measured in megapascals. A sample of 20 porcelain specimens was taken and the bond strength measured. Part A says to use Excel to calculate the sample mean for each repair kit and create a side-by-side box plot. What do you predict the outcome of the ANOVA to be? Well, it's interesting because Part A is actually done automatically in the web app, but we'll go ahead and use Excel, okay, to do this, and so that we can make a little prediction before we use the web app to actually calculate the p-value. I'm going to call each of these groups, I'm going to number each of the groups, right? So Cojet's group 1, Sillastor's group 2, and so forth. And we want to calculate the sample means of each of these things. So let's head over to Excel and see what we get for each of these sample means. Okay, so we're on the bond strength example. I'm just going to go ahead and compute the sample mean below each of these columns. So we'll say equals average of the Cojet group. Same thing for Sillastor. You could do all these means by hand, I suppose. It would take you a lot longer. Okay, so there are the means. That's an interesting, that's interesting. It looks like Cojet and Sillastor have a similar sample mean, and it looks like Samara and Ceramic Repair have a similar sample mean, but it looks like there's a wide gap between these two groups, if that makes sense. We were also asked to do a side-by-side box plot, so we can try to do that. Let's see. I'm going to insert. I'm doing this from my iPad, so some of this is a little different from the way that it looks in the desktop version of Excel, but I think if I go to charts and I want a box plot. Where's a box and whisker? There it is at the bottom. So if I do box and whisker, okay, then I get this nice side-by-side box plot. And yeah, you know, it seems like, oh, you know what okay, so yeah, so I get this nice side-by-side box plot. It looks like, yeah, Cojet and Sillastor are kind of in the lead, and then Samara and Ceramic Repair have a smaller bond strength, right? So that's reflected in our sample means. Anyway, let's write these things down. So 16.28. I think it was 17.64. 10.64 and 10.78. And the box plot, we're not going to redraw it. What would you predict well, I would predict that we're going to reject the null hypothesis in the ANOVA, since it looks like there's a difference between this set and this set, right? So I would predict, I predict that we will reject the null hypothesis in the ANOVA. Only one way to know for sure, though, and that's to actually run the test. So let's do it. The null hypothesis in an ANOVA is that the means are the same for all of the groups that you're comparing. We're comparing 4 groups. The alternative is that at least one mean is different. Okay, step 2 is to collect the sample evidence, which we've already done, right? So that's done for us. Step 3 is to get the p-value. We'll go to artofstat.com. The app we're going to use is called ANOVA. One way. And of course, we don't have summary statistics to feed into it, so we're just going to enter the raw data and then see what the p-value is. Now, part C asks us also to click on pairwise comparisons and confidence intervals and then interpret what we see. So I'll make note of that, and we'll just do that while we're over there in the app. Okay, let's do it. So I'm going to copy and paste each of these into the Art of Stat web app. I don't want to compare two means anymore, so I'm going to keep scrolling down until I get to ANOVA one way. That's this app right here. And I don't want to do an example from the textbook. I have my own. We need to tell it what number of groups we have to compare. We have 4 groups, so I'm going to change that to 4. And I can label the groups. I think we had Cojet was group 1. And I have the data for that. Control V. We have Silastore. For group 2. Group 3 was Samara. I don't know if I'm saying these names right, but that's okay. And then group 4 was ceramic repair. Okay, let's go get the data for the other 3 groups. Okay, so I've got all those in there. And by the way, the variable that we're looking at is shear bond strength. Okay, we get a p-value of 0.0023. Notice that the sample means are all computed for us, which is kind of nice. But our p-value is this. This is our test statistic, 7.545, in case you're asked for the test statistic. And in the ANOVA, the test statistic follows a distribution called Fisher's F distribution. So the test statistic is F equals 7.545 in case you're asked for it. But our p-value is 0.0023. We were also asked to click this little button that says pairwise comparisons. Maybe before I do that, let's comment on this. So our p-value is small, right? We're going to reject the null hypothesis. So what we can conclude from this is that there is sufficient evidence to say that at least one of the means is different. Now, the ANOVA does not tell us which mean is different. It only tells us that at least one of the means is different from the others. To determine which mean is different, one of the things that we can do is look at the sample means, which we've already done. And we've already kind of hypothesized that Cojet and Silastore are in one category, and Samara and ceramic repair are in a separate category, and there's a wide gulf between those 2 categories. That's kind of what we feel like is going on. We can change the plot type to a box plot, take a look at these side-by-side box plots, and kind of determine the same thing, right? Cojet and Silastore are up here, Samara and ceramic repair are down here. But another thing we can do, if we click on this button that says pairwise comparisons and confidence intervals, then we will get all of these. What the app does is it does head-to-head comparisons using a test called Tukey's test. Okay, and you can look at the p-value for each of those head-to-head comparisons, and you also, these lower and upper bounds are confidence intervals for the head-to-head comparisons. So looking at Cojet versus Sillistor, for example, the p-value is large, which indicates we won't reject the null hypothesis. There's probably not much of a difference between Cojet and Sillistor, which corresponds nicely with kind of what we said. Cojet, Sillistor, yeah, they have similar means, okay? But when you compare Cojet and Samara, you get a p-value of 0.04, suggesting that, okay, there is a large difference between Cojet and Samara, okay? Kind of like what we thought. Similarly for Cojet versus ceramic repaired, Sillistor versus Samara, etc. Samara and ceramic repaired don't seem to have much of a difference between them because they've got a large p-value. So this all kind of confirms what we kind of suspected going into the problem. So let's write some stuff down. So our p-value here, 0.0023. 0.0023 is less than alpha. So we reject H null. Okay, we're rejecting the null hypothesis in favor of the alternative. So we would say at least one of the repair kits has a different bond strength than the others, right? There is sufficient evidence to conclude that at least one of the repair kits at least one repair kit has a different mean shear bond strength than the others. And that's really all we can conclude. That's all we can conclude from the hypothesis test itself. If we want to get more specific and say, well, which repair kits do we think are the best or whatever, well, then we would have to do a little bit more analysis, take a look at the sample means, look at the pairwise comparisons, right, and all of that stuff, which we've already done. And so the interpretation that I would get from that is it seems that Cojet and Sillistor are similar in bond strength, and that Samara and ceramic repair are similar in bond strength, but there's a wide gulf between those groups. If you were asked, which repair kit would you suggest to somebody who is, who wants a really strong bond? You would say, well, either Cojet or Sillistor, right? There's not much of a statistically significant difference between Cojet and Sillistor, but there is a statistically significant difference between Cojet, Sillistor, and Samara ceramic repair, right? Samara and ceramic repair are significantly less strong than Cojet and Sillistor. So you would recommend Cojet and Sillistor, right? Unless the prices are different. Like it could be the case that maybe Cojet and Sillistor are better and consequently they're more expensive, right? Or something like that. And so if you're just trying to suggest a cheap fix to somebody, well then maybe you would say Samar ceramic repair, depending on the prices, right? But if you were going off of bond strength alone, then you would say Cojet and Silastore are about equally good, and they're significantly better than Samara and ceramic repair, right? That's what we would say. One more example. This data set you're definitely not going to want to type into the calculator by hand, I would say. Thankfully, we can just copy and paste it from Excel into the web app. But this one is about live births. It says an obstetrician knew that there were more live births during the week than on the weekends. She wanted to determine whether the mean number of births was the same for each of the 5 days of the week. She randomly selected 8 dates for each of the 5 days of the week and obtained the following data. So 10,456 live births on some Monday, right? And so forth. So this is really kind of a fascinating example to me. Just the fact that there are more live births during the week than on the weekend. It seems strange because it's like, well, wait a second. You can't determine when your baby is born, right? The baby comes when the baby's ready to come, right? But it would appear that there is possibly some wiggle room. So that's kind of an interesting thing that we'll think about a little bit more. We have a follow-up question that's going to ask us about that. But go ahead and pause the video. See if you can run the ANOVA on this one. Here's my solution. I'm going to call each day of the week. I'm going to label each day of the week, right? So Monday will be day 1, Tuesday day 2, and so forth. And the null hypothesis is that the average of live births is the same on each of these 5 days of the week. The alternative is that at least one mean is different. Just looking at the numbers, to me, it does kind of seem like Monday is a little bit lower than the others. But the only way to know if that's statistically significant is to run the test. I'm not going to make us write down the sample means, I think, but that's what we would do in step 2. Let's go ahead and get the p-values. We'll be able to see the sample means when we get the p-values anyway. So we'll go to artofstat.com. We'll run the ANOVA test. And we're just going to enter raw data. And doing that should give us the correct p-value. So let's head over to, let's do that. So first we'll go over to Excel so we can grab our data. Then we'll go over to artofstat.com. Let's reload this. I want to do my own example. We have 5 groups to compare this time. Group 1 is Monday, Tuesday, and the response that we're measuring here is number of live births. Okay, let's go get the rest of the data. Okay, and there we have it. Right now we have a dot plot. We could change this to a box plot if we want. And yeah, the box plot really reveals that, yeah, Monday seems to be the clear outlier here. The other 4 weekdays seem to be pretty similar. Wednesday maybe is a little bit lower than the others. And that's reflected in the sample means as well, right? Monday has by far the lowest sample mean. Wednesday is the next lowest, but it has over or a little under 1,000 more live births than Monday does. So anyway, that's really interesting. We have a tiny p-value, right? Less than 0.0001. And I think the clear outlier here, as I've said, is Monday. If we wanted to be absolutely sure if maybe Wednesday isn't different from the rest, we could look at these pairwise comparisons. And we could look at like Tuesday versus Wednesday. Yeah, it's a small p-value, but not really small enough, right? It's not less than 0.05. We could look at Wednesday versus Thursday, Wednesday versus Friday. Yeah, none of those are small enough to say that there's really much of a difference. The ones that are all small are the ones that are comparing Monday to other days of the week, right? So Monday is the clear outlier. Monday is the reason that we would be rejecting the null hypothesis here. So our p-value is less than 0.0001. Okay, if you haven't paused the video to do this on your own, pause it now. Write out the decision and conclusion for this test. But we should be rejecting the null. We're using the 0.01 level of significance. 0.0001 is less than 0.01. So reject H null. There is sufficient evidence to conclude that at least one of the days has a different mean number of live births than the others. And again, that's all the ANOVA would allow us to conclude. But we can look at the sample means, we can look at the box plots, we can do the head-to-head comparisons, and we can see that really it's Monday. It seems to be that Monday is the day that has fewer live births than the rest, which I guess we could go ahead and answer part C, and we'll come back to part B. But it says, do any days stand out as having a significantly different number of live births? Yes. Monday appears to have significantly fewer births than the other days of the week. Okay, and then we're asked what might account for this. Again, I kind of teased this earlier in this problem, but it's like, doesn't the baby decide when the baby's going to come? Right? You can't really decide when the baby's going to come. So why should it be the case that fewer babies are born on Mondays than on Tuesdays or Fridays or whatever? And I think the answer to that question is probably because, well, there is some control over when babies are born, because some babies are born via C-section, and C-sections are typically scheduled in advance. So if you have an obstetrician who doesn't like to deliver babies via C-section on Mondays, then, the obstetrician will schedule the birth for Tuesday or Thursday or whatever, right? And so if people in general tend to have a negative attitude towards Mondays, which they tend to do, then it makes sense that doctors would schedule fewer births on Mondays insofar as they have any control over when births occur through things like C-sections. Or another example would be like, sometimes labor is induced, right? So the doctor will give the mother some kind of drug that will induce labor and get labor rolling. And maybe they're just less likely to give them that drug on a Monday because they don't want to have to, deliver a baby on a Monday. So I think that is what accounts for it. So we could say C-sections, right, cesarean sections, and induced labor might account for this. Because otherwise, it's really hard to explain why a baby would not want to come on a Monday, right? It's not like the baby knows. Although maybe, I don't know, maybe the baby absorbs the negative energy from the mother or something. I don't know. Anyway, but we skipped over part B, which asks us to, what does the p-value mean in this scenario? Well, the p-value, the interpretation of the p-value is the same as usual, right? This is the probability that we would obtain the sample means that we obtained, which we didn't write down, but you can see them in the web app, right? The sample means that we obtained, okay, if the null hypothesis were true, so if all of the means are the same. So we'd say, if we assume that there's no difference in the number of live births on each weekday. So no difference in the number of live births on each weekday. So if we assume that there's no difference in the number of live births on each weekday, then there's a 0.0001 probability. So a really low probability. Actually, it's less than that, right? It's less than 0.0001. Then there's a 0.0001 probability that we would see such a large difference in our samples. Okay? It's just not likely that we would observe such a large difference in our samples if we assume the null hypothesis to be true. And so we reject the assumption and conclude that, well, it must be the case that at least one of the days has a different mean. Okay, so that's the ANOVA. And that'll do it for tests for means. I think we've introduced all of the tests that we have for proportions, and we've also now introduced all the tests that we have for means. We introduced the one sample t-test in section 3.2 and 3.3. And then in this section, we introduced the two sample t-test for comparing two means from independent samples. We talked about the matched pairs t-test for comparing two means from dependent samples. And then we talked about the one-way ANOVA test to compare more than two means to each other. In order to know when to use a two-sample t versus a matched pairs t, we need to determine whether the samples are independent or dependent. With independent samples, the way that one sample is obtained is not determined by the way the other sample is obtained. With dependent samples, the samples are linked, okay? Examples would be like befores and afters, husband and wife, twin A, twin B, right hand, left hand, right? These sorts of things. Each individual in a dependent sample has a matched pair in the other sample. One dead giveaway, if you're looking at two samples and they have different sample sizes, then they cannot be dependent samples. They can't be matched pairs samples. For a matched pairs sample, the sample sizes have to be the same. Now, if the sample sizes are the same, then the samples could be independent or they could be dependent, right? And so to distinguish between those, you just have to read the context of the problem and see if the way that the first sample was obtained automatically dictated the way the second sample was obtained. So that's two sample T versus matched pairs. The ANOVA, I think we made the point that the ANOVA is analogous to the homogeneity of proportions test. In fact, we could call the ANOVA test a homogeneity of means test if we wanted to, but typically it's just called an ANOVA, analysis of variance. And we don't have an analog to the goodness of fit test for means. And that's it. That'll do it for this section. Thank you for hanging in there. It was another long one. But we'll talk some more about some other inference in the next section.